Saxon's Calculus, Lesson 71 is applications of the definite integral. For the first time, we're going to discuss it. So it starts out by saying that in today's science books, distance is measured in meters and forces are measured in newtons. Mechanical work is force times distance. So if a block that weighs 3 newtons is moved vertically upward a distance of 4 meters, 12 newton meters of work is done, because 4 times 3 gives you the 12, and then the words carrying with are the newton meters. So then a newton meter, everyone got tired of calling it that, so they changed its name to a joule. The work done is represented by the area of the rectangle on the left that they pictured there, where F is the force in newtons and X is the distance in meters. And then they're showing you that it's the same with 12 joules, 12 kilometers, and so forth there. Yep, so then they're just saying the same 4 kilometers per hour times 3 gives you the 12 kilometers. That's how they got it in the second box. Now, let's jump to example 1. A steady force of 50 newtons is applied to an object to move it 100 meters. What is the work done by the force? So we know that we need to integrate to find the work done, and we are going from 0 to moving it 100 meters, so 100. I'm just going to put the meters there even though we're not using it when we plug it in. It just kind of helps me keep it organized. So steady force of 50 newtons. Okay, so my equation then is 50x. No, 50 dx, good grief. When I integrate, it's 50x. That's what I meant. And now we're plugging in the 0 to 100. So 100 times 50 is, of course, 5,000. And then 0 times that is 0. So I have nothing to subtract off. So my answer is 5,000 joules. Example 2. A variable force, F equals 1/2 x squared. So I know I'm going to be integrating the 1/2 x squared with the dx, is applied to an object to move it 6 meters. So in other words, go from 0 to 6. So there's my boundaries, 0 to 6. What is the work done by the force? Okay, so we're going to integrate, add 1. That's going to make it 3. So 1/3 and 1/2 is going to make a 6x cubed. Plugging in the 6 as the higher. I'm having more trouble doing that in my head. (36 times 6). 1 second. Okay, definitely can do it that way. I don't know why, it doesn't matter. 6 squared is going to be 216, but I'm dividing it by 6. So it's basically taking off one of those and just doing 6 times 6 is 36. So 36 joules answers that question. Talk about complicating something simple. Example 3. In example 2, how much work was done by the force in moving the object from the 4 meter mark to the 6 meter mark? So it is exactly the same thing that we just had with this 16x cubed, except now the boundaries are 6 and 4. Okay, well my 6 we already knew went to 36, and minusing, plugging in the 4, so 4 times 4 is 16, times 4, 64, dividing by 6, 10 and something. It is 10 and something. I'm going to write it as 64/3, however. Just a second. I got that from the book. Let me triple check something. 4 times 4. Yes, that was the 64. Mine is over 6. Common denominator of 6 would be the 216 minus 64, that's 100 and something. Oh, for a calculator to use while doing this. 52, 152 over 6. Definitely reducing by 3. That'll take me to a denominator of 2. Goodness gracious. No. Dividing by 2 takes me to a denominator of 3. 2 goes into 152 76 times. 76 over 3 joules. There we go. All right, now that we're not cramming things into a tight space, maybe I can be better. Example 4. Simon calculated that the velocity of the object would equal 1/2 t squared plus t meters per second, where t is the total time elapsed in seconds. Approximately how far would the object travel between the 5th and the 7th seconds? So I know I'm integrating from the 5 to the 7. I guess I should have put that over here. Then, yes, okay. So now let's work that out. So that would be a 1/3 with a 1/2, so that's the 1/6 t cubed plus 1/2 t squared. Plug in the 7. Oh, 7 times 7 is 49 times 7. I hope 343. For always putting it in. That should be divided by 6. So 343 over 6 plus 49 over the 2. That's the higher 7 plugged in minus the lower 5 plugged in. 5 times 5 is 25. 125 over 6 plus 25 over 2. Common denominator of 6 multiplied by 3. I think 6, 3, 1575. 10, 9, 4, 125. Okay, plus that would be 200 over 6. And that's a positive, and we're minusing that, so that should be fine. Are we getting anywhere close with 290 over 6? Don't know yet, because their answer is in decimals. 48.34 is where we're headed. Joule, no, not joules, meters. Okay, let me see if maybe, so 6 would go in there about 4 times. Yes, I feel like if you divided that, that should be approximately where you get. Yikes. All right, example 5. Hooke's law for perfectly elastic springs tells us that the force on a spring is proportional to the displacement of the spring from the position of rest, or F. So they're giving us F equals Kx. And then it continues where constant K is the spring constant. If the spring constant for a spring is 1/2 Newton per meter, how much work is done in stretching the spring from 3 meters to 4 meters? So I know that I'm going from 3 to 4 on the meters. And the equation they gave us was a half for the constant. So that gives us a half x. Plugging in here with the dx, then integrate, so we get x squared. So that's going to take it to a fourth x squared. Plugging in our 3 and our 4. 4 first. 4 squared, 16, divided by 4 is 4, minus 3 squared is 9, 9/4, common denominator 4, so 7/4 joules. All right, that's lesson 71.